we discussed about two-wheeled robots, this differential drive, but we saw that there is a need for a balancing point. That's why tricycles or robots with 3 wheels are also very popular, because then the third wheel is kind of like a balancing point as well, so it's stable on the floor. The way these robots work is that there are still the 2 wheels with the same axis of rotation. Now, in this case, they're not powered, they're not driven. Okay? And they can still rotate independently, so that we can ensure that they will follow the same angular velocity. And instead of the 2 wheels changing the velocity, we have 1 wheel that we can change its orientation, and we can also change its velocity. Okay? The third wheel is usually between the other 2, and more in the front or in the back. That's how you see it. Okay? The idea is exactly the same. We have our trajectory, we see where is the instantaneous center of rotation, what's the distance until the center, and we try to control where the center along which the robot will actually rotate. How do we do that? We do that by changing the angle, the steering angle of the front wheel. Okay. Now, as we saw earlier, that the 2 wheels, when we had the 2 wheels, they had to have the same angular velocity around the same center of rotation. The same is true for the 3 wheels. All 3 wheels have to have the same center of rotation. Okay? And we saw that basically the center of rotation is at the perpendicular to the tangential of the velocity of where the robot is heading. The center of rotation will always be perpendicular to all 3 wheels. Okay, and because these 3 wheels, they will form a triangle, I can always locate the position, I can change the position of this instantaneous center of rotation by changing this angle. Okay, you can see if the front wheel is where the red is, the instantaneous center of rotation will be on the left side. If it's how the blue wheel is, it's going to be on the right side. Okay? And by changing the values here, I change where is the center of rotation. Now, can we calculate the distance of the center of rotation from the center of the robot? Can I calculate this distance? How? If I know angle alpha. So I have basically this triangle. Okay, this is my... Okay, I know this distance, I have it as d. Okay, I know this angle, alpha. And I want to find out what is this distance. Can I do it? How? What do we know? Which angles are the same here? First of all, this is perpendicular. Okay, what else is perpendicular here? Or, yeah? The red one with? The red and blue are, red, the 2 red are when this is the wheel. Okay? So these the 2 red are together and the 2 blue are together, but for different angles alpha. Okay? So they're not in the same time, they don't exist. So the 2 red ones. Right? We said that this will be perpendicular to the wheel. Good. We know this angle. So what else do we know? This one. Y. if two angles have both their sides perpendicular to each other, then they are the same. Here I have perpendicular this to this, and I have this to this. Okay. Another way to see it is that this alpha will be the same as this one, and if this is perpendicular, this will also be perpendicular. So this is 90 minus alpha, and this is also 90 minus this one. So it will be the same. Okay, so this is alpha. Good. And can I know this distance? If I know this angle and this distance? How? The tangent is great. So R will be D, right? Yeah, you're right. My bad. D over alpha. Okay. Or if I take this angle, I can put them inverse. Basically, that's what I'm doing here to make it so I don't have the tangent down. I take the pi over 2 minus alpha. So it's this angle, beta, and this tangent is this over this. So it goes inverse. This is correct, but then tangent of B of beta, which is tangent of pi over 2 minus alpha, right? Beta is pi over 2 minus alpha. Okay? This is the inverse of this, R over D. So we get to that. Okay? So I can control this distance by controlling this angle. What happens when alpha is 0? So when I'm pointing straight, where do I expect R to be? Infinity, right? When alpha is 0, this becomes 0, so this will become infinity. The same thing here. When this is 0, tan pi over 2 is infinity, right? What happens when when alpha is 90 degrees? So in the weird case that the wheel points to the left, 90 degrees, so this will be 0, so this will be 0, basically, R. So R will be here. Okay? Now, how do we write the angular velocity around this center? Okay, I need my famous formula. By now you must have been bored. I need this formula, okay, where my R is basically this distance. Now, let's call it something else. Let's call it R small. We have R big here. Okay, so the angular velocity of this thing will be related to the linear velocity at this point with this distance. Okay, what is this distance? What do we have there? It's basically this square plus this square, right? Okay. Or another way to write this is like this. This alpha. Okay. Now, one small detail here: this omega w and uw. Omega w is the angular velocity of the wheel. So w is from wheel, and this is the linear velocity of the wheel. And these are, yeah, mistakenly I put there R. This R is the diameter of the wheel again, as in the previous example. Okay. So yeah. And this omega is the angular velocity of the robot, not of the wheel. So I have these two equations, and so this is in the frame of the robot. As before, if I can control the linear and angular velocity of the robot by changing this alpha and the linear velocity or angular velocity of this wheel. Okay, and in the frame of the worlds, I use the same thing I did before. I take the linear velocity in the frame of the robot and I transform it in the frame of the world. I just multiply with the cos and sinus, okay, of this theta, and the angular velocity in the world frame and in the robot is the same as before. It's equal to this as it was here. Okay. So again, I have some equations that tell me how can I change the linear and angular velocity in the world frame by changing what? The linear velocity of the wheel and this angle alpha. And if I want, I can use this equation to do this with the angular velocity of the wheel. Just change this with omega w times r, omega w times r. Okay? Very simple. What I want you to remember is that, yeah, all these calculations are done by cutting our trajectory into calculating the instantaneous center of rotation all the time and controlling this velocity so that we match the desired instantaneous center of rotation. What about the inverse? As I said earlier, we can just do the equations from these two equations. For instance, if we divide them, what do I get? I get tangent of A if I take this one over this one. Let's write it quickly. So it is theta equals to omega w d sinus of alpha, right? And y is omega w cosinus of alpha cosinus of, no, sinus of theta, right? Yeah, sinus of theta. I solve for alpha by taking this over this. So I will have theta over y dot equals the u will go away, right? So I'll have 1 over d sinus theta. And here I have tangent of alpha. So alpha will be arctan of theta d sinus theta over y. Okay, so now for a specific velocity in the y direction and angular velocity, I know what should my angle alpha be. And similarly, I can do the same for the linear velocity. I just take one of the equations, this equation for instance, and I solve for u. Now alpha I know from the previous equation, so it's like the inverse kinematics that we did for robotic arms. Okay? It's a lot of trigonometry and concepts that you already know, so nothing very complicated. But it's nice to know how these things are calculated for mobile robots. And that the concept of degrees of freedom, inverse, direct, geometric model are the same. Okay? We could equally do the dynamic modeling as well. We're not going to do it today. But how could we do it? Let's say in principle, we already saw it for the robotic arms and for the drone. What would be the approach? We're right there. Yeah, the Lagrangian. Okay, the kinetic and potential energy. In this case, potential would be probably always 0 if we're moving on a flat surface. could consider like this. So we just have linear and angular velocities. Okay, how do we calculate linear and angular velocities in the world frame? Using this, we do the derivations and we end up with a dynamic model. Same thing as with the drones and as with the robotic arms. I'm not going. This is even simpler. Okay, and then we can use the dynamic model to do control. Okay. Very quickly, four-wheel robots. I guess you've all seen four-wheel cars. It's very, very useful. One little detail, based on what we know now. What do we need? Well, how do cars work? They usually have the front wheels driving and the back wheels moving independently. There are also inverse with the rear wheels being driven, or there are also four-wheel drive, right? What is the condition that should be respected? As before, the same rotation for all three wheels, right? Four wheels. Yeah. So what does this mean in this case? When I turn left or when I turn right, do these wheels need to rotate the same or by different amounts? Let's see what would happen if they would be the same. If I have a car, okay, now my back wheels are fixed, so for sure my center of rotation will be passing around this line, okay, because they don't rotate normally in cars. Now, if I have the same angle here and here, oops, sorry, I would end up this one rotating here and this one rotating here. Okay, this is not what happens, because then you would hear your tires squeaking all the time, right? So this means that these wheels have to turn slightly differently. Which one more, which one less? This one more, this one less. So it rotates less and it falls at the same point. Okay. Next time you see a car with a steering wheel turned, check the wheels that they are not turned exactly the same. Okay, this is called the Ackermann drive. What? Seriously? No. No, that's how cars work. You're dragging or... Okay, the springs. Okay, I see. Yeah, no, it's how cars work. Otherwise, you wouldn't have the same center of rotation. Now you know why, right? You would have a different center of rotation, and the car would slide, basically. It wouldn't move smoothly. Okay. They also have some other angles. Anyway, the Ackermann drive is more complicated because they also rotate in this direction a bit, but that's another story. Okay. The idea is that these angles have to be different, but they still respect trigonometric relationships, which has to do with this distance, and so forth. And where do we want the instantaneous center of rotation to be? In which case are the two angles equal? Well, we'll go straight, right? Because in that case, for both wheels, we are at infinity. Left or right? Yes. Okay. How do we calculate these angles? I'm not going to go through all the equations and explain. But the idea is, again, trigonometric equations. This is the cotangent, or the inverse of the tangent. Okay? But that's basically the relationship they need to respect. D is the distance from the back wheels to the front, and L over 2 is the distance from the wheels from the center of the robot. Okay, therefore these are, what happens when A and B are 0? What is the cotangent of 0? infinite. It's the opposite of tangent. Or tangent is 0 at 0 and infinite at 90. Cotangent is 0 at 90 and infinite at 0. Okay, so this would be infinite minus infinite. Would it be plus or minus infinite? Yes. So yeah. Good. Now we see that the wheels have different rotations, and that's something you didn't notice. What about their velocities? Is it the same velocity or not? That this has to rotate and this has to rotate? No, why not? What is the relationship that they have to respect? Same what? That this angular velocity and this angular velocity have to be the same. Okay, what is this angular velocity? It is this linear velocity of the left wheel and the distance of the left wheel, and the linear velocity of the right wheel and the distance of the right wheel. Okay, so we have something like this basically. So for each one is u equals omega r. Okay, so I have u L over RL equals u r over r. What is RL RR? We see how we calculate it there. If this distance square plus this distance square square root. So we can calculate this red and blue line trigonometrically. But the two, there is like a slightly different velocity on the two wheels as well. And that's also how cars work. Okay, maybe that's also you don't know. This is what the differential of the car does. Distributes the speed left and right according to how much you rotate. Okay. Otherwise, the car would slide. Not good. Too much noise. Now, how do we describe the kinematics of this? So we could use the same approach. What we do is we simplify a bit things, and we consider a third wheel in the middle, a fifth wheel in the middle, okay, which would need to rotate. If we had, let's say, 3 wheels here in front, then each one should respect this relationship, okay? So we consider a virtual wheel here in the middle, and we can calculate how much this angle should be in order to fall on the same center of rotation. How do we calculate it? Either this or like this. We'll get the same value. Okay? And then we can forget the red and blue wheels, and we do the modeling as we did for a tricycle. Okay? We calculate how gamma should be in order to do our kinematics, and then we say, okay, if I know gamma, I can calculate how much is alpha and beta. So we fall back to a other situation. Same for tricycle with steering angle gamma. Any questions so far? So that's what we had to do with the modeling on using the kinematic modeling of mobile robots. And I promise that we will talk, if we have time, about planning, trajectory planning, and I think we have time. So if you don't have questions, I'll change the topic and go to planning. Ooh, yeah, no. I can tell you in principle how it works, but, and it's not so difficult anymore, but it's basically an inverted pendulum. It's an inverted pendulum problem. So you have a thing like this with a mass, and you can move this left and right. Right? I guess you've talked about this problem, the inverted pendulum as an unstable, I don't know, control theory maybe? No? A bit? And how to stabilize it? You consider several stuff like, springs and dampers here and so on, but it's basically a problem like this. Maybe for the way I draw the robot here is not so visible, but if you think a Segway, where it has like really a thing here, a human even, it's this problem. And what the robot does is basically moving back and forward using the two wheels and trying to balance itself. It does nothing else. Okay, so if you have a controller smart enough to balance this thing, then that's what the Segway does basically. Okay? Or all this fancy skateboard stuff that you see, I know the one wheel thingy, it's the same thing. Basically moves itself a little bit forward and backward. You don't really feel it, maybe, unless you're really shaking. But it tries to balance the mass here. And because the mass usually it's smart, human, it also has some, feedback by itself. So it also tries to balance itself out a bit. So the problem is not extremely difficult. But that's what it does. And how does it do it? I don't know. Probably you have modeled this process somehow. There is a dynamic model, and there is some controller that is trying to keep, I don't know, this theta equal to 0. It has some encoders where it measures the actual theta. Did I satisfy your curiosity? Very briefly. Did you hit yourself, or you were not on top of it? Okay. Yeah, I don't know. If you want, we can discuss about the actual thing, but in principle, that's how it works. In principle, that's how it works. It just moves itself back and forward and tries to stabilize the mass on top. It's like how you're doing, you make me do acrobatics again. You have this thing, and how you're trying to balance it, you move it back and forward. Right? I'm not in the camera, I hope. So you do this motion. Now, implementing it practically, it's a totally different story, but okay. Now, why do we need planning on robots, specifically for mobile robots? What does planning mean, or what? To move around. Yeah, and we usually want to avoid obstacles, to avoid crashing, yeah. And also find an optimum way of going, because usually mobile robots, they are not connected in the battery, then they're not very mobile, unless they have a very long cable. So yeah, optimality and efficiency is very important for mobile robots, right? Especially if we're talking about robots in Mars, where we cannot just give them more battery. Yeah, so ideally we want to find the most efficient way of going to a place. Either it is the shortest amount of time, or the shortest distance, or you can take into account more consideration. I don't know, if it's a steep curve, then it more consumes energy and so on and so forth. But the basic idea here that we see is how to avoid obstacles, basically. Okay, full of obstacles, efficient ways. And let's say we have a situation where I have a robot here, and I want to go here, and I want to avoid these kind of obstacles. Okay. So the input for the planning is basically, we need to know how the robot looks like. If I want to avoid obstacles, I need to know how big I am and so on. And also how it is the environment, and where do I start and where do I have to go, in a way. So this is like the input of a general planning algorithm. The output is the path that the robot should follow in order to reach that goal, according to optimality. So there are different approaches. I put them here all on the basically some names, and we'll see what do they mean and how do they work. Roadmap approaches, where we have like a set of possible paths and we eliminate, or we try to find the best among those paths, or cell decomposition, or other potential field strategies where they ensure optimality and so on, or where we have like bug algorithms. They work like bugs, like an ant walks around, discovers, oh, it's not a good way, I don't know, doing like trial and error kind of thing. Okay, the idea with the roadmap approaches is that how they usually work is that after we know the information of the environment, we try to find optimal ways in a very basic way. We construct these lines of sight where we connect our initial position and our target with all the corners of the objects that we see. For instance, here you see. And then we do it not just from the initial and end position, but from all the corners that we actually see, we connect lines and so on. Okay, and then what do? We choose the one that is the shortest one, let's say, by combining these lines. Now, what problems would we have with this case? Can you imagine some? Yeah, okay, we might have missing information. But let's say that's the problem for any planning algorithm. If you don't know how the environment looks like, then you will always have issues, unless you keep on rediscovering it. Maybe. Okay, but how would we? What would we do here, for instance? I would need like a million points on the surface, because what I did here is I took corners, and you know, if I have round stuff, then I don't have corners, or I have too many corners, you know, and then it becomes like computationally, as you say, a bit silly to do this stuff. Okay. Another approach, again, roadmap, is this called von Oroi diagrams. It's basically von Oroi diagrams. How do they work? You give points. So the input is these points, these dots that you see here, and you construct areas where each area is closer to one of these points. So this whole area here, the closest point of any point to this in this area is this initial point here. Okay, the moment I go a bit higher, then this point becomes closer, basically. Let's say, okay, all this blue area, the closest of the initial points is this point here, whatever. So we use kind of like the inverse, where we take the obstacles and we construct points that are equally spaced from the obstacles. Here, the walls of the room are also considered an obstacle. Okay, so this point has equal distance from here and here. For instance, this one has equal distance here, here. This one from here, here, and so on. And based on these points, we construct basically a path somewhere close to the target, and so on. And this also ensures that we will have like enough clearance. Clearance meaning like I have a safe distance from the obstacle, because these points are always equally spaced from all the obstacles. Basically, they're in the middle. Yeah, that's why you would use another technique. Let's say this thing, which also goes very, very close. Of course, all these techniques are, you know, they have their advantages and disadvantages, so you use them in different cases. Yeah, or you could use a different metric, for instance. So here we see that this is the metric is that the distance is equal from both sides, or I could have different metrics where it would give me like more curved stuff and so on. Whatever. of how to calculate these center points, basically. Another approach is called this cell decomposition, where we take vertical lines from the edges of all the objects and of the room. We assign numbers. We construct like a graph of how could I go to each one of the areas, and then figure out which one is the shortest, basically, which has the less nodes. And we go from the middle points of those nodes, basically. More interestingly is this motion planning with the potential field, which is more like, these are, more or less whatever, very childish or very basic planning methods. When we use potential fields, basically we use mathematics and we try to find an optimal situation. Basically, we construct a function. Let me show you a function, or let's see this stuff. Okay. We construct a function that is, you can imagine like a quadratic function that looks like a bowl, and I put the center of the bowl at the target where I want to reach. Okay. And then I construct some other functions for each obstacle where they have negative value from the initial function. Okay, so this function, let's say, has a attractive potential function, so it's like, I don't know, positive, while the obstacles generate functions which are repulsive, which are negative. Okay, and then I can add them together to make like a more complicated function, and the gradient of that function will ensure that I will go to where I want to go by avoiding the obstacles. So let's see how this looks a bit more visually. So let's say I have this attractive field. I have this part of the quadratic function where here is my goal. Okay, so let's say something like this. It's a quadratic function. And I have some other functions where I have my objects, where they are repulsive, so they have like values on the opposite direction. Where I have an object, it's a very, very big value, and close to the object I have some smooth function that is going back to 0. Okay, and by adding the attractive field and the repulsive field from the obstacles, I get like a more complex function that, if I have my starting position of the robot somewhere here, let's say, and I try to optimize and find where is the minimum of that function, I will follow a trajectory that will avoid the obstacles, and probably it will follow an optimal path along the until I reach the minimum of this function. This would have been stuff you would see next semester if you were from the other direction. Because now you are in the Informatica Applicata, or the other one? You are Informatica Applicata, right? And the other one is Automatica, yeah. We do optimization of these functions in the Automatica, but this year I think not. I think not. Anyway, the idea is that you have an initial point and then you do some numerical optimization to find where is the optimum, and you usually go from one point to the next, the next, the next, the next. But this optimization avoids, let's say, fields where you have like very big values. So that's why it's used, and it gives us an optimal path in a way. Now, if you want to include energy efficiency and so on, you can add more you can construct more complex functions where, I don't know, maybe here, let's say, in this region I have an uphill, so I can also include that to somehow make my optimization try to avoid it. And other complex situations that you might want to include in the function and optimize. And this will give you like a mathematically optimal trajectory, while these methods will not. Okay, but these methods are computationally much more easier than something like this. So maybe For an application, they're good enough. For another application, might not be good enough. Okay, questions. This is more like general knowledge. It's not something super important for now. Any questions? No? Okay. How was the lab last week? Did you like it with the control? Did it work? You had the control of the two joints robot with a potentiometer, right? So next week you will do the same with the drone. You will control the drone. We have the dynamic model and you will implement the controller. No. Yeah. We are working on adding like hardware as well. Like we bought some robots this year. They're still about to deliver them. Whatever. 2 months ago we ordered them. Anyway, so that we have like a physical robot next year. Not. Yes. True. Yes. Don't fail the exam. So no questions? Okay.